Today we'll finish precise exceptions and hopefully cover out-of-order execution fully also. But before that, homework 4 is off today. It's due after the spring break, but I strongly recommend that you do it in preparation for the exam, because these are topics that will be covered in the exam, and you will learn a lot if you do it earlier. Lab assignment 4 is also off today. Again, start early. You'll have control flow to what you did previously. Yes.
In comparison to lab 3, how long lab 4? About the same?
That's a good question. I don't know.
It should be pretty easy if you set things up right.
Okay.
Yeah.
But still start early. and this is also an individual assignment. So I'll write that down next time. Okay. And you know that lab 3 is due this Friday, right? And I hope you all are done with it. Or people who are not here are actually doing the lab 3, you think?
Yes.
Yes, really? That's not good. They should learn about out-of-order execution too. Okay. Maybe we'll have to find a solution to that, because attending the lecture is important, right? That's where you learn the concepts. If you don't attend the lectures, how will you learn the major trade-offs and concepts? Because we cover a lot of things that are not in the book. Like, for example, what I will cover will not necessarily be in the book today. Okay, feedback sheet. Well, I'm preaching to the choir here, obviously. You guys are all here. Please turn this in. Even if you cannot turn it in today, please turn it tomorrow. Turn it any time. We want feedback from you, basically. A little bit about the midterm. You know that it's in class next week at this time. And it will start at 12:30 sharp and end at 2:20 p.m. sharp, because there's a class after us. It's closed book, closed notes, and I told you that you can bring a single cheat sheet. All topics we covered can be on the exam. Everything is fair game related to the course so far. And we have a bunch of buzzwords, actually, that are supposed to aid you to study. I recommend you go through those buzzwords. In fact, some of those are more than buzzwords. Looks like my TAs added explanations of the concepts as well to make your life easier. But lectures, labs, homeworks, required readings, everything is covered. And the test will consist of a variety of problem-solving, design, and trade-off analysis questions. We will put up some sample exams from 447 previously, but this is the first time I'm teaching this course, so the exam style will be different. So we will also put up some exams from the advanced computer architecture course that I taught earlier, and you will see we will have the style will be similar to a mixture of both. Okay, and homeworks will help, of course, for you to prepare. One thing I should emphasize: come to class early. If you can come at 12:25 p.m., that would be the best, because we will end at 2:20 p.m. sharp. If you come late, then you're eating from your own time. Okay. Well, okay. And a reminder, I know you guys are busy doing labs, but if you're interested in solved errors and how they affect system design, especially in terms of errors in DRAM, main memory, this could be an interesting seminar to attend. Okay, this is a review of last lecture. We had a brief detour into n-modular redundancy. So I expect you to know that now. Dual modular redundancy. That's an easy concept. And you can do the trade-off analysis. What are the upsides, what are the downsides, right? What are the advantages of using true modular redundancy versus no redundancy? And what are the downsides of doing that? We finished control dependence handling in pipeline machines. And I'll not go through that because I have a lot to cover. We talked about precise exceptions and interrupts, and we started that. And we'll continue with that today, and we'll cover out-of-order execution. Any questions before we start? No? Okay. Nothing on n-modular redundancy? Okay. So remember that we wanted to preserve sequential semantics. And pipelining essentially violates that sequential semantics, right? Because, well, the strictest sense of sequential semantics. You start an instruction before you finish the previous instruction, right? And if you actually do some writes in the middle of the pipeline, as opposed to delaying them at the very end of the pipeline, then you can even violate the semantics by updating the architectural state in an inconsistent way. So we wanted to avoid this. And the issue becomes most prevalent when you have multi-cycle execution units. Right? If everything took single cycle, then you could update the state at the very end of the pipeline. And you wouldn't run into issues of one instruction that's coming later in the instruction stream updating the state earlier than another instruction that's coming earlier. So multi-cycle execution makes it a little bit difficult because you can have multiple different functions that take different number of cycles. And remember this picture that I showed. In this picture, there is something wrong with it because what happens is if you allow this to happen, which means an add instruction that comes after this long latency floating point multiply updates the register file before the floating point multiply is complete. If the floating point multiply incurs an exception somewhere around here during its execution, now you have an inconsistent state in the program because you updated registers with these 3 instructions, actually with these 5 instructions, right? They're all written into the register file before this floating point multiply has written. Make sense? So we don't want this to happen. Sequential semantics of the ISA is not preserved in this case. Then we had a brief detour into exceptions versus interrupts. This is an exceptional condition, right? I will not go through this, but exceptions and interrupts are fundamentally different. Exceptions internal to the program, interrupt is external to the program. Internal to the program you need to handle right away, right? When you detect it. And when you know that it's not speculative, right? And we'll see what that means. Interrupts you handle when you have a convenient time. For example, if the keyboard is interrupting the processor, maybe you handle that interrupt after you finish all of these instructions. Right? You wait for a while. You drain the pipeline, for example, before handling the interrupt. You insert no ops for a while, and then once the pipeline is drained, you go and handle the interrupt. Whereas you don't have that luxury, if you will, if you incur an exception in this floating point multiply, because the pipeline is already full. Right? Okay, so you should know the difference between exception and interrupts. So the idea of precise exceptions and interrupts, we covered this at one of the very early lectures, right? The von Neumann model. The architectural state should be consistent when the exception or interrupt is ready to be handled. Now what does this mean? If you're at the processing of some instruction, let's say, let's do the multiply here, and then add. If this multiply incurred an exception and you're ready to handle it, then you'd better make sure that it looks as if, well, multiply is not completed obviously, so it looks as if all previous instructions have completed and none of the later instructions have completed at all or have even started execution. That way, what you can do is you can essentially just save the program counter at this point, floating point multiply, jump to the exception handler, and come back to this program and restart executing as if nothing happened, if you will. Right? Because you have the precise state of the architectural registers and memory at this point. Whereas if some instruction over here has written and you don't have the precise state right at this point, now you cannot easily come back, right? You can come back and you're going to re-execute this instruction that's already written, right? So it may update the state again and it could have effects that you don't want it to have. That's why precise exception is very important. So that's the idea of precise exception. All previous instructions should be completely retired, and retired will become more clear. This is retired is the same as complete. Retired, I guess, update architectural state. State that's visible to software. This is register and memory. Okay? Well, I guess I have it already there. So sometimes you will see commit also used for this. Okay, so why do we want precise exceptions? Just to get back to the motivation for this. Well, first of all, you can say that the semantics of the von Neumann model ISA specifies it, and you have to obey the ISA, right? Period. But why does the ISA specify it? Remember von Neumann versus data flow? let's contrast data flow with von Neumann. In data flow, everything executes, an instruction executes when its data values are ready. Which means that you don't have a sequential state in the program. Which means that you don't know when you stop the program what your state is, right? You'll have an inconsistent state. One time you stop the program versus the next time you stop the program. You can get very different states because you don't have this control boundary that tells you this is the state I'm looking for at this point in program. Does that make sense? Do you remember this discussion? Okay, good. So I will not go into it further. But that's the key. This is one of the motivators, if you will, that I want to use. So remember, it's very difficult to debug this machine, the data flow machine, because basically instructions execute in data flow order, and their data values become available. And this data flow order really depends on the latencies of execution, which are variable. Right? And at some point, one instruction incurs an exception. Now, what is your state at that point, right? If you're debugging this program, when you run the program, you encounter a bug, for example, or you want to stop the state. At some point, how do you define that state? Even it's very difficult to define that state because that requires the definition of which instructions should have executed at that point. Whereas with control flow, you don't have that problem. So precise exceptions, the major reason for having precise exceptions is really it aids software debugging. So if you're debugging this program, you really want to have precise exceptions as a programmer because you really want to know whether the effects of the instruction that you're stepping through, let's say, is done or not done. It would be very confusing if the effects of some other instruction was exposed to you while you're single stepping through these instructions. Okay. Does that make sense? So if you, for example, single step through this floating point multiply, you expect this floating point multiply and only this floating point multiply to change the architectural state. You don't expect some instruction downstream to change the architectural state. It would be very tough for you to figure out what happened in your program if some other instruction changed the state because your pipeline was designed, it happened to be designed in some way. Make sense? Okay. So there are other benefits to it. It enables easy recovery from exceptions, and we will see page faults for later on. And you can imagine this, right? How do you recover from a floating point multiply exception? Basically, what we do is we ensure that no instruction, including the floating point multiply, and after that updates the architectural state. We save the program counter, and that's it. And we have the architectural register file and memory state at that point. And we can get back to that state very easily later on and restart from that PC. So this enables restarting. Whereas if you allow some of these other instructions to update the state, it becomes harder. It's not impossible, but it becomes harder to restart this program. Why does it become harder? Well, let's say you allowed this add to update the architectural state, R4. I don't remember what it wrote to. And you allowed some other add to update the architectural state. Maybe what you do is you keep a record of what you allowed, what instructions actually updated the architectural state. Right? When you incur that exception, you don't have a precise state, but you also keep a record of, in hardware, what instructions update the architectural state out of order, if you will. Does that make sense? And when you get back to the state, maybe you somehow skip those instructions. Now, I'm not suggesting this is a viable solution as I described it, but you can imagine ways of actually enabling this with imprecise state. Basically, you're really reconstructing the state when you come back if you do this. Well, one thing you could do actually, you don't necessarily need precise exceptions, right? What you can do for this purpose, for restartability purpose, what you can do is you can actually dump the entire pipeline state somewhere in memory. And when you come back, you restore the entire pipeline state. You can imagine that way of handling exceptions, right? But then you'll need to tweak some things, of course. You'll need to ensure that floating point multiply executes again, perhaps. So there are other ways of ensuring restartability, except they're very hairy, if you will. You don't want to dump the entire machine state somewhere, entire microarchitecture to somewhere in memory, probably, right? It's a lot of state and it's a lot of useless work. Whereas precise exceptions makes it much simpler. Okay, so it enables easy recovery, easily restartable processes, and traps into software also. For example, software implemented opcodes, right? If this opcode was not implemented, you could easily call the software and run a routine that implements it and then come back without worrying about what instructions afterwards actually update the architectural state. Precise state makes it a lot simpler. Make sense? You can think about some of these concepts. I understand this may require a little bit deep thinking, if you will. And there are actually machines that dump the entire pipeline state before people figured out solutions to handling precise exceptions in the way we will describe. Okay, so one way of how do you ensure precise exceptions in pipelining? One idea is to make each operation take the same amount of time, right? So basically eliminate multi-cycle, eliminate variability in the execution of different units, like this. Basically, if your longest latency operations multiply, make sure all of your adds also take 8 cycles. Good idea? You're shaking your head. I guess not. Yeah, it's a bad idea, right? But it works. I mean, it ensures that you write to the architectural state at the very end. The downside is basically you're now extending the operations unnecessarily, right? What if each memory operation takes 500 cycles? We ensure that each functional unit also takes 500 cycles. Okay, it's a bad idea. So there are people have proposed other solutions, and I will cover 2 of these that are used in modern processors. Actually, checkpointing is also used in modern processors, but I will not get into that. Reorder buffer and future register file. And you can read this paper that has introduced these concepts, as well as this paper that has introduced the checkpointing mechanism. So, one idea, instead of doing this, we still allow instructions to complete out of order, but if an instruction is completed out of order, we don't allow it to update the architectural state yet. That's the idea of the reorder buffer. Basically, we ensure out-of-order completion of instructions at the end of the execution unit, but the update to the architectural state, register file, and memory happens in program order, which means that we insert something at the back end of the pipeline called the reorder buffer that reorders instructions. Here, instructions come out of the functional units in an out-of-order. They go into the functional units in order, but they come out of the functional units out of order because of multi-cycle execute, right? And there are different cycles for different functional units. A multiply takes 8 cycles, an adder takes 1 cycle. But before we update the register file and memory state, we say this instruction has to become the oldest in the machine. Right? That's the idea of the reorder buffer. It's relatively simple, conceptually simple, right? You reorder the instructions before updating the architectural state. So how does this work? Basically, when an instruction is decoded, it reserves an entry in the reorder buffer, and the entries are in sequential order. When the instruction completes, so you have this reorder buffer that keeps track of the oldest instruction and the youngest instruction in the machine in program order. When an instruction is decoded, it reserves an entry starting with the youngest instruction. When the instruction completes at the end of the functional unit, the instruction writes its result. This is the result, and this is the destination register for this particular instruction into the reorder buffer. And when the instruction becomes the oldest instruction, and if it's complete, So there needs to be some bit saying that this instruction is done now. Then, only then, the result is taken from the reorder buffer and written to the destination register. Make sense? So basically what we have done is, instead of writing the register directly from the functional unit, once the result becomes available, we're delaying the writing of the into the register file until the instruction becomes the oldest in the machine. Make sense? That way you ensure in-order program updates, in-program order updates. Of course, then the question is, what happens if an instruction has an exception? So you have an exception field, if you will, in a reorder buffer entry. This is set if an exception is detected anywhere in the pipeline here. So if the instruction is done and it has an exception, then what we can do simply is, and if this is the oldest instruction, now it's simple, right? We've ensured that none of the instructions that come after update the architectural state, and all of the previous instructions that are done are already out of the reorder buffer. They've already updated the architectural state. And so we have a precise state at this point, right? Now we can handle the exception very easily. We have the precise state, and we have a program counter, which we should probably store also here, of this instruction in the reorder buffer. Make sense? Simple, right? Okay. So that's how we preserve the precise state. Okay. Well, so what's in a reorder buffer entry? I've given you a partial example here. Well, obviously, you need to know whether the entry is valid or not. So we have a valid bit here. You need to know which destination register the instruction is writing to. You need to know which, once the value is produced, what is the value that is to be written to the destination register. And of course, for stores, you need to have the store address and store data. Right? If it's a store, again, we want to ensure all the instructions update the state in program order. So you need to store the store address and store data. We want the program counter so that if the instruction incurs an exception, we'll come back to it. We'll save the program counter. And did this instruction incur an exception while it's flowing through the pipeline? So while the instruction is flowing through the pipeline, if an exception happens, we don't handle that, right? Why not? I tell you this as if it's true, but if I'm wrong, challenge me. So you have this pipeline, fetch, decode, execute, and multi-cycle execute different function units, right? And then everybody writes to the reorder buffer, and an instruction actually finishes when it's the oldest instruction, and it's done, and it has no exceptions. Then it gets out of the machine. So if an instruction incurs an exception right here, and if it's not the oldest instruction, it just sets an exception bit here, right? We don't want to handle it right away because we don't have the precise state for that instruction, right, at that point. Not only that, this exception may not be a valid exception, right? What if a previous instruction also caused an exception? Then this exception is really bogus, right? Because you shouldn't have, according to the von Neumann model, you shouldn't have even fetched this instruction. Make sense? So exceptions become architecturally visible when the in-program order also. And reorder buffer enables that as well. Basically, anytime you need to update the architectural state in program order, this is a general mechanism to enable that. Okay. Also, you need val bits to keep track of the readiness of the result. So this is more complicated than I showed here, because you need to ensure that the instruction is completed. So there needs to be a complete bit somewhere, I think. And you need to ensure what type of instruction it is. You know what type of instruction it is so that the reorder buffer writes to the correct place. So if it's a store instruction, it should write to memory, right, at the end. If it's a add instruction, it should write to the destination register. Okay? So there needs to be bits, val bits, and control bits specifying what should the instruction do when it's the oldest instruction and it's done. So essentially what we've done is added a pipeline stage at the very end. When the instruction finishes, it writes to the reorder buffer. And every cycle, there is a finite state machine that checks this reorder buffer if the oldest instruction and checks what happened to the oldest instruction. If the oldest instruction is not done, nothing happens. If the oldest instruction is done, then this finite state machine checks for exceptions. Let's assume there is an exception, then what happens is the finite state machine starts handling the exception. How do you do that? You flush the pipeline and save the program counter and jump to the exception handler. We will see this briefly. If there is no exception, then the finite state machine looks at what the instruction is doing. Let's say it's writing to the destination register. It takes the destination register ID from this entry and the destination register value and writes that into the register file. If it's a store, it takes a store address and store data and writes it into memory. Make sense? Okay. So this is a new pipeline stage, if you will. Okay. So how does this work? Well, now what we can do is we can still have variable multi-cycle execute for different instructions. This is the same example that I showed you. This is the floating point multiply. And this is the add that comes after it. Now we have fetch, decode, execute, write to reorder buffer stage. And this is the commit stage, if you will. This is write the result from the reorder buffer to the register file or to memory. Now, if you see this part, the write to the register file or memory are all done in order, in program order. And this while until the instruction becomes the oldest, it just basically sits in the reorder buffer. Okay. Well, I guess one question is, what if a later operation needs a value in the reorder buffer? So this instruction has completed, and its value is really available, right? It's sitting here. Well, I guess if we have to take that example, this is the f multiply. It's not done yet. And let's say it's not going to cause an exception. The next instruction is an add. At this point, it has written, it's done. It has written into the reorder buffer, and it's written a value x to register destination, if you will. Well, it wants to write. And the value is available. What if a later instruction wants to read from destination register? Let's call it register 1. Well, one thing you could do is you could say that, sorry, it's in the reorder buffer, so you're not going to get this value, so stall the pipeline, right? If you have a scoreboard at the beginning of the pipeline. You can also update the scoreboard when you write to the scoreboard, which is fine. Right? But, I mean, this, of course, reduces your performance opportunity. Right? Could be another independent operation can actually read this value and continue executing. Well, one idea is you can actually read the reorder buffer in parallel with the register file. Right? Remember? When we fetch the instruction, we read the register file, after we decode the instruction, of course. Now we can also read the reorder buffer. Make sense? So if the instruction is looking for register 3, for example, let's say we're decoding an instruction that needs register 3. And there is a previous instruction in the reorder buffer that wrote to register 3. In the register file scoreboard, this value is not available because there is an instruction in the pipeline that's going to write to register 3. And it's not written into the register file because it's sitting in the reorder buffer. So one thing we could do is we could search for register 3 in the reorder buffer. So any instruction that's decoded searches for register 3 in the reorder buffer. And how do you do that? Well, this is content-associative search. Right? You need to compare the destination register ID of each entry in the reorder buffer with the source register ID of the incoming instruction. Because this reorder buffer is not organized like a register file, right? It's really the program order, the instructions stored in program order. So this search is a content-associative search. Basically, reorder buffer becomes a CAM, content addressable memory, where you search based on the destination register ID. Basically, you try to check whether the destination register ID matches the source ID of the instruction in the decode stage. And if it matches, and if the instruction in the matching entry is done, then the value is ready. Right? You can take that value and start executing the instruction that you're decoding here. And thus you're enabling forwarding through the reorder buffer in this case, right? Because the value is already available. Make sense? Well, not so easy, right? Is this a simple CAM? Talking too much, I guess. It's your turn. What is complicated about this? Yes?
What if there are more than one instruction that are writing to the register?
Exactly. What if you have multiple instructions writing to R3? It's becoming interesting, right? This instruction wrote to R3, and you have another instruction writing to R3. Well, it shouldn't have executed anyway, right? If you have a scoreboard that says, oh, there is a value that's right, that there is an instruction that's writing into R3 here, and if your scoreboard stalls on a write after write dependency, this instruction shouldn't have gone into the reorder buffer because you would have stalled there. Right. But that's kind of dumb also, right? You have all the machinery to continue execution, and this is not a real dependency. Why stall the pipeline? So what you said makes sense. Makes sense, and we will get to it. So actually, there will be multiple instructions writing to R3 because we will eliminate this dependence on write after write. So if you have an instruction that's writing to R3, you can enable another instruction that's also writing to R3 to go into the pipeline. Right? And reorder buffer actually gives you a nice way of doing that. Because this CAM, you can modify this CAM to ensure that it's an ordered CAM, if you will. Ordered content addressable memory. Which means that you get the latest version of R3 that's matching. Basically, you not only search for R3, but you need to find the latest one matching. Because you don't want to forward from the middle one, because that disregards the program semantics. Okay? Well, there's a bypass path over there too. Okay. So there's one more thing that I should tell you about the implementation of this. What if you run out of the entries in the reorder buffer? What if your oldest and youngest come here? Right? What do you do? Like you cannot have infinite entries in your reorder buffer, right? You have to ensure you need to recycle entries, but still you need to preserve order. Which means that this is really a circular buffer, right? Basically, it's a circular buffer of the instructions in program order. So your oldest can become here, whereas youngest is here, right? Does that make sense? In hardware implementation. So you need to account for that also when you're actually doing the forwarding. Does that make sense? So you need to do a circular compare. Yes?
So having the oldest and youngest is basically like when you start the
Yes, basically, when you decode the instruction, you allocate a reorder buffer entry. Instructions are allocated entries in program order.
Okay.
Here. That's the key. If you allocate entries in out of program order, then you're out of luck, right? You lost the program order. Okay? And an instruction, of course, carries its reorder buffer ID throughout the pipeline. I haven't got into these implementation details, but you have an instruction should carry its reorder buffer ID so that it can write its result to the correct ID. Correct entry. Okay. Well, one other thing you can do is actually, so this is an expensive search. So this could actually lengthen your cycle time. You're accessing the register file in parallel with the reorder buffer, and reorder buffer access is a little bit complicated. It's a content addressable search, ordered content addressable search, and a circular buffer. And also you have this bypass path coming from the function unit so that you can get your data, which means that you can actually lengthen your critical path significantly. So one idea to simplify this access is to use indirection. You can access the register file first. You can change the register file a little bit. If the register is not valid, then the register file can store the ID of the reorder buffer entry that contains or will contain the value of the register. So we're going to change the register file a little bit. It will have a valid bit, and it will have the reorder buffer ID, and it will have the value. If it's valid, then the value is to be trusted, right? Now, when an instruction is decoded, it sets the destination register's valid bit to 0. And remember, when an instruction is decoded, it allocates a reorder buffer entry. So now, in the reorder buffer, we have the oldest, we have the youngest here. Let's say this is entry 25, this is entry 5 here. When instruction is decoded, it takes its reorder buffer entry and sticks it into its destination register. Destination register's reorder buffer ID field in the register file. So now we've linked this register to a reorder buffer entry. Okay. What are we saying here? If the value of this register, let's say this is register 1. Register 1 is not valid, but instruction that's at reorder buffer ID 25 is going to produce that value. Right. Does that make sense? Now we know a way of getting this value when it's produced. R1 is not in the register file, but you can actually get it from entry 25, from the reorder buffer. If it's ready, of course. If it's done, if the instruction is done. Yes? So you can do this for this indirection mechanism, but we will do this for data forwarding later on also. To ensure. We're actually, right now what we're really doing is renaming the register, if you will. Right? So you will see that this is the concept of register renaming. We're saying this register, here's one copy of each register. This register is not here, but you can get it from here. Now what we've done essentially is renamed register 1 to reorder buffer entry 25. Yes?
What's the value?
So we will see. We will see the value. But here, the value is, you can enable the indirection, right? What you can do is you can access the register file first, so that we don't search the register file and reorder buffer at the same time here. You can access the register file first. If the value is not there, then you can go to location 25. And if the value is there, actually, then you can get that value and continue executing. Yes?
I'm actually like, what's the 500 over time?
Oh, okay. So this was earlier. It's a stale thing.
Okay.
So if the val bit is 0, then you don't care what the value is, right?
But if it's 1, then you get that value.
Yeah. If it's 1, then you get the value. Okay? So this enables the indirection because now we store the reorder buffer ID in the register file. And we use that to access the reorder buffer if the register is invalid. Now this also simplifies the access of the value from the reorder buffer, right? Now we know exactly which location in the reorder buffer is going to supply the data. So we don't need to do a content-associative search in the reorder buffer. Does that make sense? Because a previous instruction that was producing R1 wrote its reorder buffer ID here. Let's say we're fetching an instruction that's reading R1. Then it knows that the instruction that wrote to R1 is at reorder buffer entry 25. So what it can do is it accesses the register file in decode stage, sees that this is invalid, then it accesses the reorder buffer with the reorder buffer ID, and if the data value is done, if the instruction is done, then it can get the value from here. Okay? Okay, I'll skip this here to simplify further part. Okay, so let's take a look at this. So we can actually eliminate output dependencies using this mechanism, right? If you look here, floating point multiply rise to R4. This is the same example. We're still at the same example. Add also rise to R4. What is R4's value at the end when someone needs to source R4? Well, you'd better like it to be this, right? Not this. But, and you can ensure that an instruction that's dependent on R4 gets the correct R4 if you use this mechanism. Whenever an instruction writes to a register, it writes reorder buffer ID to the register file. Right? So if there are multiple writers to R1, let's say another instruction wrote to R1 here. Then all that instruction does is it changes the reorder buffer ID to its own reorder buffer ID, 38, let's say. And it's decoded. Yes?
So, as you get instructions that are running the same registry, you just update that which one's working.
Exactly. Exactly. We just update the pointer, if you will, to the reorder buffer. So you always know at this front end of the pipeline what is the latest value of R4. Or R1 in this case, of any register if you want. Which reorder buffer entry is going to produce that value. And you know that the next instruction, because you're fetching in program order, is going to get that value, right, if it's sourcing that register. So essentially what we've done is we've eliminated this false dependencies. Remember, output and anti-dependencies are not true dependencies? There's nothing really R1, if you're writing to R1 with this add, and if you're doing multiply, writing to R1 with this multiply, and somebody's sourcing R1 here, there's no real relation between this add and multiply. Assume that there's no dependency going into that also. This R1 has no relation to this R1. The reason we had R1s here because the compiler somehow ran out of registers. But now what we've done is we've provided more registers. This reorder buffer is bigger than the register files. We have 32 here. But now you can have many copies of R1 here. And they could be written by different instructions. So this is the idea of register renaming. This eliminates, well, my word told you that. The register ID is now renamed to the reorder buffer entry that will hold the register's value. Is the register ID is mapped to the reorder buffer entry ID, as we've done here. And similarly, you can think of this as architectural register ID. This is the architectural register ID. When you're decoding the instruction, you're looking at the architectural register. Is mapped to a physical register ID, if you will. You can think of this as a physical register file, although it's not organized that way, right? You contain the values of the registers here.
Yes? About that, just one case I was thinking was if you have two, like let's say over there you have adding to R1 and then a multiply that goes to R1.
Okay.
And right after the multiply there's an instruction which uses R1.
Uh-huh.
But the register file would have the wrong R1 value, right? It would be pointing to the one executed by R1. Since the
one executed by what?
The value of R1 that is stored after the add in the buffer.
Okay, here?
Yes, so that's what the register file will be pointing to until multiply finishes executing, right?
No, multiply changes the register file when it's decoded, right?
Okay.
Multiply. So this needs to be updated in program order, right?
Okay.
When the instruction is decoded, not when the instruction is executed.
So it will still stall right after that until multiply is executed.
What will say stall?
The next instruction that's using R1.
That's right, exactly.
Okay.
Next instruction will wait for this entry here. Okay. So this illustrates anti and output dependencies, right? Basically what we're doing is we're giving the illusion that you really have a large number of registers, right? Because you're not limited to only one value stored for R1, if you will. There could be multiple copies of R1. Think about a program that keeps writing to R1. It's not a realistic program, but let's say there are no dependencies in the program. This is the program you have. What will happen is you will allocate entries in the reorder buffer for all of these instructions, and you can execute them because they're not dependent on each other. You can execute them in parallel, in a pipeline manner, right? Without having this multiply to store for this add, without having the next one to store for this. Because there are no true dependencies, if you will. These are all false dependencies. As long as they write their values to some space, if you will, and you provide that space, this program executes correctly. Yes?
Are you saying this is for super scalar stuff, or is it still pipeline?
This is still pipeline. Yeah. This is still pipeline. Basically, after you send this instruction to the execution unit, you can send this instruction to the execution unit. And then you can send this instruction to the execution unit. But the same principle works for superscalar also, right? As long as you detect the dependencies in parallel. Okay. Okay, we will get back to this renaming in out-of-order execution, because this is the key enabler of out-of-order execution, really. You really have a mechanism for eliminating the output and anti-dependencies, and this also gives you a way of linking the instructions that are dependent on previous instructions. Right? Now you can say an instruction that's sourcing R1 after this instruction is decoded should get its value from reorder buffer entry 38. And when the instruction that is assigned reorder buffer entry 38 produces its result, what it can say is, oh, I'm producing my result. And my ID is reorder buffer entry 38. Anybody waiting for this result? Get this value. That's the idea of out-of-order execution. You can link dependent instructions using this new name you assign to the value, if you will. But we will get to it very soon. Okay. Okay, so this is the final in-order pipeline with reorder buffer, if you will. We have fetch and decode stage. At the end of decode, an instruction accesses the register file in the reorder buffer and allocates an entry in the raw. Well, I'll call it the raw reorder buffer. It's commonly called the raw. Checks if an instruction can execute. If so, it dispatches the instruction or sends the instruction to the functional units. That's a term that I introduced here. Execute instructions can complete out of order. At the end of completion, when instruction completes, it writes its result into the reorder buffer. And there is a separate state, retirement commit, that checks for exceptions for the oldest instruction. If none, it writes the result to the architectural file or memory. If there's an exception, then it flushes the pipeline and starts from the exception handler. So this is an in-order machine, in-order dispatch, or scheduling, or execution machine. This is usually called an in-order machine, if you will. But it has out-of-order completion of instructions and in-order retirement of instructions. Retirement means update of the architectural state, if you remember. So, pros and cons of reorder buffer. It's conceptually simple, right? You reorder instructions before updating the architectural state. It can eliminate false dependencies, as we've seen. The con is, well, it needs to be accessed to get the results that are yet to be written to the register file. Okay. You can either use a CAM, which is a bad idea, as we've seen here. Actually, you might want to design this for your next homework, if you're excited about it. Or you could use indirection, which is nicer, but then it increases your latency. Anytime you add in the indirection, your latency increases, right? So you have to access this first and then this next. So can we do better? Well, there are people that propose other solutions, and I will cover one of them that we will use later on for out-of-order execution also. Well, the idea is the future file. Who said that we need to keep one copy of the file, right? Why don't we keep two register files? One is for the front end, and one is for the architectural state. Architectural register file is updated only in program order, and its main purpose is to support precise exceptions. And we use a reorder buffer to ensure in-order updates. We introduce a new file called the future register file. This is updated as soon as an instruction completes. Assuming, of course, the instruction is supposed to write to that particular register. Right? Now, the purpose of the future register file is to have fast access to recently produced values, to the latest register values. It's also called the front-end register file, if you will. The purpose of the architectural register file is to ensure you can recover the state on an exception. That kind of register file. So let's take a look at how this looks like. Now we still have the reorder buffer to ensure in-order updates to the architectural register file, but we now just have the future file. The advantage of future file is, well, what do you have in the future file? Again, the same thing. Almost. Value. I'll call this the tag now, and data. A tag could be the reorder buffer ID. It could be anything, really, as long as you ensure that an instruction has a unique tag. Well, I forgot to update this, basically, but ignore this for now. So what is the advantage of this? Now you don't need to access the reorder buffer, right? You don't really need to access the reorder buffer in the front end. You just need to access the future file. Because when an instruction completed, it sent its value into the future file. So you don't need to go to the reorder buffer, do a CAM or indirection. It's already in the future file. Does that make sense? Yes?
Why do we need the
Why?
buffer then?
Well, you do need the reorder buffer because you need to update the architectural file in program order. You don't need to update this in program order. The purpose of this is different, to get the value quickly. Right? So how is this updated? Basically, when an instruction at reorder buffer entry X writes to a register, it sends X, and if the tag matches X, and if the value is not valid, then the data is updated. Right? Yes? No? No question. Okay. Okay, I'll update this, so ignore this for now. It's assuming I have covered the history buffer solution. Like, you don't need to know about that. There are other solutions to this problem. Okay, this is clear? Yes?
Wouldn't we still need some sort of a reorder buffer in the future file in the case we have different length executions, like the really long multiply writing to R3 followed by add that writes to R3? So the shorter add would write to the future file, and then later on the longer multiply.
Aha! That's excellent. That's why we have the tag. Right? So, okay, let me explain this. I guess you're saying F multiply, right into R3, and then a short add, right into R3. Remember, so when this F multiply is decoded, it allocates a reorder buffer ID. Let's say reorder buffer ID 25. And when this is decoded, it allocates a reorder buffer ID 26, let's say. So F multiply writes to R3, makes R3 invalid, and writes its tag 25 here. Data we don't care about, right? Because it's not valid. The next instruction, add, just updates the tag, right, to 26. Does that make sense?
So it doesn't eliminate the added latency of getting down to the reorder buffer.
Exactly. Yeah, it doesn't eliminate the added latency. Okay. Now, okay. So that's the idea. You get the values fast. I'll let you go through this, but it's very in an in-order pipeline with future file and reorder buffer is very similar to an in-order pipeline with reorder buffer, except in decode stage you access only the future file, allocate an entry in the reorder buffer, and check if the instruction can execute. If so, dispatch the instruction to the function unit. Execute, instructions can complete out of order. When the instruction completes, it writes its result to reorder buffer as well as the future file. So there should be another path here, really. So it's not only writing to the future file, reorder buffer, but also to the future file. On retirement, we check for exceptions. If none, you know what to do. Else, we flush the pipeline, start from the exception handler, and also copy the architecture register file to the future file. That way you have the architectural context correct. Well, if you jump to the exception handler, you don't need to do that perhaps. But your architectural register file is the real architectural state. Future file is really used for forward of the values quickly. Okay. So before we move to out-of-order execution, hopefully we've covered a lot of the concepts that readied you for that. I'd like to cover a little bit how we handle exceptions. Yes?
My question was, you said like, let's say value gets updated later on, and then it gets announced that this value is updated and can be used. Could that not lead to too much of a build-up? There could be too many instructions waiting for that value.
That's right, yeah.
And it could. So how would you counter that kind of a build-up in the system? And potentially, you could have really bad execution times overall.
Well, it's better than stalling the pipeline at the beginning, right? At least you're allowing the pipeline to move, and you're ensuring that instructions that need to wait for the value to wait. So yes, you need to do extra work, but it's better than stalling the pipeline once you see the dependency, right? Right after right dependency.
So we get part of the work done, but not everything. That's
Exactly. And you will see, I think this will become clear when you see out-of-order execution fully. Okay. So let me finish this and we'll take a break and then we'll go into out-of-order execution. So what do you do when you have detected an exception? Basically, when the oldest instruction ready to be retired is detected to have caused an exception, what do you need to do? You need to recover the architectural state, register, file, IP, and memory. And that's easy to do if you have precise state, right? You already have it, hopefully. You flush all the under instructions in the pipeline, save the instruction pointer and registers as specified by the ISA, and redirect the fetch engine to the exception handling routine. Remember we talked about vectored exceptions? Basically the exception code specifies where to vector to. That tells you where the exception handling routine starts. Okay? I'll actually skip this. But you can handle branchless predictions in a very similar way also. I'll skip the stores also for now. We'll get back to it in out-of-order execution. So let's take a 5-minute break and then we will get into out-of-order execution. All you've been looking forward to, right, this semester? Yes. Well, you now know how to do it, actually, how to design it. I'm giving you the basics, but not giving the full picture. So this is, we'll talk about out-of-order execution. This is also called dynamic instruction scheduling. It's called dynamic scheduling because you decide the schedule of execution based on dynamic events rather than static instruction scheduling that's done by the compiler. Static scheduling, compiler gives you a schedule and you execute instructions in that order. Right? Dynamic scheduling, you don't have to obey that schedule. You can actually figure out which instructions can be executed and execute them before other instructions that are not ready to be executed. And you've already seen the concept, right? The concept is really, if an instruction's data values are ready, and if you know that, and if you can keep track of that, you can execute that instruction. It's really data flow. That's the idea. Right? So the idea is really schedule the instructions in data flow order. Of course, we're going to do it in a way such that the programs are not written as a data flow graph. The programs are still sequential. It's like a sequential assembly program that you write in MIPS. And we're going to extract the data flow graph out of it, if you will, dynamically, to enable the execution of instructions that are ready at that point in time. Okay, so this is the review of the in-order pipeline that you've seen. The problem with this is a true data dependency stalls dispatch of younger instruction to functional units. Okay. Remember, if you encounter a true dependency, when you decode an instruction, we stall the pipeline. Now that's a bad idea, right? If you want to improve pipeline throughput, why stall it? The dispatch, I've already told you about this. And we're going to get rid of this problem. We're going to ensure that true data dependencies do not stall the pipeline. Well, I guess you can look at these. Just to demonstrate this, this add that's truly dependent on this multiply, integer multiply, stalls the pipeline here. Here, again, if it's a long latency load and this is an add, when you decode the add, the whole pipeline is stalled. Even though these blue instructions are all independent, right? They're all independent of the load or the add. So you could potentially execute them. Well, the difference between these two code portions, there is actually a difference between these two, and I'll cover these quickly so that we can get to the meat of the material. The latency of the load is variable. It's unknown until runtime. Right? Whereas the latency of the multiply is fixed. Right? Although you could imagine multiplies with variable latency, depending on the source register values. Right? There are machines where multiplies sometimes took 1 cycle, sometimes took 8 cycles. Why would that happen? If one of the source values is 0, you can easily compare that source value to 0 and figure out whether you actually need to do the multiplying. Right? Assume that that's not the case here. So actually, multiply latency could be variable too if you implement that. But let's say that its latency is not variable. If its latency is not variable, then the compiler could do a better job reordering this code. If this was a smart compiler, it wouldn't put the add here, right after the multiply, because there are independent instructions that are not going to affect execution. Well, I guess this add is independent of this add. So I did a bad thing here. Huh? Okay, you cannot move this add over here, but you could move this add and unmultiply before the red add. Okay. Whereas here, the compiler doesn't know, right? Is the cache miss? We don't know until runtime. So how do we prevent dispatch stalls? You've actually seen several ways of doing it. Let's see if you can remember. So preventing dispatch stalls, what does it mean? A true data dependency, right? You cannot dispatch an instruction if it has a true data dependency on something else that is already in the pipeline. We're not talking about false data dependencies. We're kind of eliminating them. We're going to hammer that home soon. But true data dependency. You've actually seen ways of eliminating these. Or you've actually seen ways of not stalling the pipeline when you have a true data dependency. Any guesses? Fine-grained multithreading, right? You don't stall the pipeline. Value prediction, you don't stall the pipeline. You have to do something else, but don't stall the pipeline, even if you get a true data dependency. Well, fine-grained multithreading, you don't even get a true data dependency, right? Because you're ensuring that you never have this dependency in the pipeline. And compile time instruction scheduling or reordering. Again, you can ensure this, right? As long as the compiler can find independent instructions or insert logs. Well, hopefully you know the disadvantages of the above three. This is a good question for preparation for the exam, by the way. We've covered these concepts quite a bit. So any other way to prevent dispatch stalls? I've already given you the idea. Basically data flow, right? Somehow fetch and fire an instruction when its inputs are ready. But the problem is really in-order dispatch. So somehow we need to get rid of this in-order sending of the instructions to the functional units. We want to make sure that's done in a data flow order. So our solution will be data flow or out-of-order dispatch. And the idea is simple, right? when we fetch an instruction that's dependent on a later instruction that's in the pipeline, why do we stall? Well, we stall because we don't have a mechanism to actually move that instruction out of the way of later instructions, right? And somehow ensure that we get the correct value for that instruction. That's why we stall. So we're going to eliminate that deficiency, if you will. We're going to move the dependent instructions out of the way of the independent ones. So when you get an instruction that's dependent, truly data dependent, on an earlier instruction, we're going to move it somewhere. And I'll call this the rest area, if you will, for dependent instructions, the reservation stations. These are called the reservation stations. I'll give you a long example soon, but basically, any instruction that comes in that's dependent goes into this reservation station. Actually, I'll generalize this such that all instructions go into the reservation stations. And while sitting in the reservation station, this instruction monitors the source values that it's waiting for. When all the source values of the instruction are actually available, now we can fire or dispatch the instruction into the execution unit. Now, instructions are dispatched in data flow order. I'll tell you how you can do this. But that's the key idea. Take the instruction, don't stall the pipeline, move it into these reservation stations that can contain many instructions, and monitor, while the instruction is sitting in the reservation station, monitor if the source value has become available. Once it becomes available, once all the source values are available, send the instruction to the functional unit. That's the key idea. Benefit, now you can tolerate the latency. You can allow the independent instructions to execute and complete in the presence of a long latency operation. Yes?
What happens if, say, an add is dependent on R3, which is the multiply? Then you get, so you put this reservation station, then you have another multiply, which is right to the same register.
Yeah.
Then you end up in a process where that add never gets on.
No, you should not do that, of course, right? And this will become more clear, hopefully. That should not happen, right? You should link, we're going to link the instructions to the correct instructions, to the correct producers. Okay, so let's see what could be the benefit of this. This is a code example that I showed before. This is the, with in-order dispatch, you can execute this in 16 cycles, I think. With auto-order dispatch, Tomosuo's algorithm that I will describe, what you can do is, the second instruction, remember that it's dependent on this instruction multiply, integer multiply. Instead of keeping it at the decode stage and stalling the pipeline, calling the independent instructions, we're going to move it away. Somewhere it can wait. And this waiting will happen in the reservation stations. And now this other instruction that's independent can go ahead and execute. Okay? And this is the reorder buffer stage. And this next instruction that's independent can also go ahead and execute. This next instruction that's dependent on the previous one, again goes into the reservation station and waits. And when the previous instruction, multiply, produces R3, we'll have a mechanism to communicate R3 to this add that's waiting in the reservation station, such that when the R3 is produced, this instruction wakes up, if you will, and executes and completes. Similarly, when this R5 is produced, this instruction, this add, wakes up and executes. When both R5 and R3 are produced, actually, this instruction wakes up and executes. So the benefit is basically you save cycles, right, by moving these instructions out of the way, such that they don't stall the pipeline. So how do we enable this? Well, obviously, we need to link the consumer of a value to the producer of a value, so that we know when to start executing an instruction. Right? If we stall the pipeline, we know when the value is ready, so we don't need to do this. But if we don't stall the pipeline, we move the instruction somewhere, we need to provide this linkage between the consumer, between the producer and the consumer. If somebody is producing R3, we need to link the consumer to that producer. We've already seen a way of doing this, register renaming, right? We can associate a tag with each data value, and consumers can get that tag, and when the producer produces the value, it'll broadcast that tag, and any consumer waiting for that tag captures the value. That's the idea. by renaming the register ID, architectural register ID, to a tag, we can link the producers and the consumers using that tag. And we'll see how this is done concretely. We need to buffer instructions until they're ready, of course. Which means that we'll need reservation stations. We need to insert the instruction into the reservation stations after renaming. And instructions somehow need to keep track of the readiness of their source values. Right? So how will we do this? Well, I've already told you. Basically, an instruction, when it produces the value, it broadcasts its tag. So in this case, there's an instruction that's right into R3, and it has a tag of 26. When this instruction completes execution, it broadcasts 26, and anybody waiting for 26 captures that value. Instructions comparing their source tags to the broadcast tag, and if there's a match, then the source value becomes available, ready at that point. Does that make sense? No? Not clear yet? Okay. And when all of the source values of an instruction are ready, now you can send the instruction to the functional unit. Okay? So this is the idea of Tomaso's algorithm. This is essentially out-of-order execution with register renaming. This was first done in IBM 36091, and this is a seminal paper that described it. And I will describe how it operates. The major difference today is now we have precise exceptions on top of it. So at the time when it was designed, it didn't become popular because it didn't have precise exceptions. Which means that if you execute an instruction out of order, you could get into an imprecise state. And this was horrible for the programmers to debug. But in the mid-1980s, precise exceptions were added to Tomaso's algorithm, and they enabled the use of out-of-order execution in many machines today. So this concept that I described, in some form or other, is used in all machines of today, all high-performance machines of today. So let's see how it works, I guess. Well, I guess before we get into it, let's take a look at what we're going to do is basically, after we decode an instruction, we're going to put it into these reservation stations, and instructions will wait in the reservation stations until its source values become ready. When both of its source values becomes ready, an instruction gets fired. It executes. Once it finishes execution, it broadcasts its tag and value, which enables the readiness of later instructions that are waiting for that tag and the value. Make sense? So basically, here, renaming is in order, so that we can link the instructions in program order. Scheduling happens out of order. Basically, you schedule the instructions to the different units out of order, out of program order. And then we reorder everything at the very end, so that the commit is out of order. So we preserve the sequential semantics at the end, and we ensure that the data dependencies are correctly followed by in-order renaming. But everything inside here is completely out of order, in data flow order, if you want. Okay. So let me give you an example, I guess, of Tomaso's machine. I hope we have time for this. Yeah, we should have time. And I'll go through this concretely. Let's skip these. We already talked about register renaming. Well, we need to have a way of renaming the registers, and you've already seen something like this, right? This is going to be our register rename table. And when we decode an instruction, what we're going to do is to read its sources from this rename table and write its destination and write a tag to its destination and ensure that it becomes invalid. And later instructions now can get that tag to refer to that value that's going to be produced. Okay. So I guess instead of going through this, let me start with an example. Oh, okay. Maybe what we can do is turn this on. Say it again. Okay, let's go through one example of how this works in this piece of code. Find a good way of actually using the board. I want to start from this side, because we'll we'll go to the left, go to the other side now. How do we do this? Go up. Blank screen will make life easier, yes. Although now I have lost the code. I guess the best of all worlds, huh? So I'll write it here. So if you remember, this was our code. R3, NAT, R3, R4, R5. NAT, I guess R2, R6, R7, R8, R9, R10, multiply R7, 10, R11, R11, R5. Actually, maybe I will break this down so that I'll show you what happens with the in-order machine for this code. And then we'll look at what happens with the out-of-order machine. That's a good idea. This part. So I will not go into detail as to what happens with the in-order machine, so you should be able to do this relatively easily. Let's assume we have one adder that takes 4 cycles, and we have one multiply that takes 6 cycles. Well, I'm not going to go through the non-pipeline machine. This is really easy, right? If you have a non-pipeline machine, you can basically add up how long it takes each to. And you have fetch, decode, execute, and write back. And execute takes 4 cycles for add and 6 cycles for multiply. Let's look at what happens with an in-order machine with scoreboarding. So this is the execution timeline that I drew for you. And you can verify it if you will. Pretty simple. Basically, you stall when you get to a dependency, if you will. That's the idea of scoreboarding. And no forwarding, I think, here. That's right. Basically, you can decode the next instruction after you write the result of the previous instruction that produces the value. So it takes 31 cycles to do this. Now, if you add data forwarding to this is the one with the data forwarding, basically you can forward the data of the first, I guess, multiply to the next add once the data value is available. So this saves you quite a few cycles. 25. The total execution time on this code is 25 cycles. So this is Tomasulo's algorithm with full forwarding. Basically, I guess I'll briefly. Should I replicate this here? No. I guess I'll keep this here. Or maybe I'll do this here. So basically, I wish there was a way of actually. Oh, there it is. Okay. So we're going to fetch this instruction, decode this instruction, and it'll take 6 cycles to execute. And it'll execute because its values are available. So now let's see how it works. So if you look at Tomasulo's machine, remember, we want to enable the linkage of these instructions. This one doesn't go down. So we have the register alias table, and you will see very quickly that this is very similar to the future file. Or this is also called the register renaming table. For each register, I think register 1 through register 11, we have a val bit, we have a tag, and we have a value. Val bit says, is the value to be trusted? If the val bit is 1, then we can get the value, because the register file, or register alias table, contains the correct value. If the val bit is 0, then the value is really available, going to be produced by the instruction that has this tag. Make sense? So this is really the tag of the writer, of the producer instruction. And every instruction will have a tag. Every instruction that hasn't been completed yet will have a tag. So initially, of course, when you start the machine, everything is valid, right? It better be. And there should be dot, dot, dot somewhere here. And let's assume that the values are 1, 2, 3, 11. Okay? So when we, let's see what happens when we actually decode this multiply. When we're decoding this multiply, we're fetching this add. And we have an adder and a multiplier, and we're going to have the reservation station entries for each. So I'm going to populate this picture, if you will. Is this the multiplier first or adder? Adder. So remember, we need a place to store the instructions while they're waiting for their values to become ready. And these are called the reservation stations. And we'll have separate reservation stations for the multiply and the add. These are the reservation stations for the multiply, and I'll keep 2 of them only here. I'll call them X and Y. And these are the reservation stations for the adder. I'll have 4 of them, I guess. Because to match the program that I've written over there, and I'll call them A, B, C, D. So what does the reservation station contain? Well, each instruction, each entry contains the following. Each instruction can have 2 sources. Let's have that assumption. Each source can be ready. So it'll have a val bit. Can you guys see this? I didn't. Where I did 2 well, let's do it. So I'm going to divide this kind of in a big way here. This is for source 1. For source 1, is the source valid? If not valid, what is the tag that we're waiting for to produce that source register? If it is valid, what is the value? For second source, source 2, is the source 2 valid? If not valid, what is the tag that's going to produce that value? What is the tag of the producer? If valid, what is the value? Okay? Similarly, for this other reservation stations, for the multiplier. Value, well, that's it. Valid, tag, and value. And of course you have a val bit for the reservation station entry itself, meaning an allocated bit. So I'm going to ignore that for now. I'm going to assume if there's nothing written into the reservation station, it's not allocated. In hardware, you have to allocate these things, right? Okay, so let's actually decode this multiply first. So we have a tag, our multiply, R1, R2, right? R1, R2, and we're going to write to R3. When we decode, we first read our sources from the register file, right? Multiply reads R1 and R2 from the register alias table. So it gets these 2 entries. And what it does is it places these entries into the reservation station entry that it's allocated to. So in the decode stage, we do multiple things. Read our sources, read source registers, allocate from register alias table, allocate reservation station entry, and also we'll see something else. Place sources into reservation station entry and rename the destination register. So multiply reads source 1, source 2, places its sources. Let's say it's allocated this. The first source, register 1, value is good. Tag, we don't care because value is valid. The register is valid, and the value is 1. Second source, register 2, valid. Tag, we don't care. Value is 2. Right? Now multiplies in the reservation station. It's allocated. One thing we need to do is to ensure that for later instructions that need to source R3, they need to really refer to this multiply. Okay. So multiply now renames its destination, which means that it's writing to R3. At decode stage it says, okay, R3 is not going to be valid until I produce the result. And you can refer to this tag, if you will, and I'll call this tag as X, because multiply is now executing at reservation station entry X, or is allocated reservation station entry X, and value, you don't need to write the value anything, but you don't care at that point, right? Because the value is going to be produced new. Does that make sense? So basically now, R3 is going to be produced by the multiply that's going to execute from reservation station entry X. Okay? And any other instruction that comes after multiply that sources R3, well, add, should really get the value from this reservation station that's going to produce it, which is reservation station X. And we will see how that happens. Okay, so multiply now rename this destination register. Now at the end of this clock cycle, if you will, this is cycle 2. We write the cycles here, 1, 2, 3. At the end of this clock cycle, one other thing happens, which is there's logic sitting here in the reservation stations that determines which instructions are ready. Well, multiply is ready, right? Both of its sources are ready. So at the beginning of the next cycle, multiply is ready to execute. Make sense? So I guess now we can think ahead, if you will. We can think of what happens if multiple instructions become ready in the same cycle, right? So you have to have some logic to arbitrate for this, the multiplier. But assume that that doesn't happen right now. So that's the idea. Okay? So that's cycle 2. And I think I've written for your benefit what happens in cycle 2. So you can look at this. So multiply becomes ready at the end of cycle 2. So let's look at cycle 3. So in cycle 3, multiply start executing and we're decoding this next add and we're fetching the next add. So what are we decoding? R3, add R3, R4, R5. So let's do that. Add R3, R4, writing into R5. Again, decoding process is simple, right? First, we're going to read the source registers from the register alias table for the add. R3, R4. We're going to allocate a reservation station entry. A looks empty. Let's allocate that. We're going to put the sources into the reservation station entry. So we're reading R3, R4. First source is R3. Is it valid? It's not valid. Which means that tag matters. So the value is really going to be produced by tag X. The instruction that is the tag X. And value, I don't care at this point because it's going to come from tag X. It's not valid. The second source, R4, we read it from the register file, 1, which means that it's valid. The second source is valid. The tag, we don't care. Value is 4. Okay? And we need to rename the destination register for this add. So R5 is being written to. It's not valid anymore. And the value is going to be produced by the add that's at the reservation station A. And value is squiggle. Doesn't matter. Okay? So now we're reading this add. Again, before the end of this cycle, there's logic that checks whether this instruction can execute. Obviously, it cannot execute because one of its sources is not valid. Right? So you can imagine what the logic is. You basically check if all of your sources are valid. If all of the sources of an entry is valid. If all of the sources of an entry is valid, then the instruction can execute. So in the next cycle, this add cannot execute. Whereas this multiply is already executed. Right? Okay? So this is the same thing that I told you before. So we finished cycle 3, if you will. Looks like I have some other comments here, but I think we'll talk about that later. Now let's look at what happens in cycle 4. What are we fetching in what are we doing in cycle 4? We're really decoding this instruction, right? Add R2, R6, R7. So essentially in cycle 3, this is really waiting in the reservation station, if you will. So the next instruction to be decoded is add R2, R6, R7. Let's do that. I think you'll get the hang of it quickly. Not already. Add R2, R6, R7. First, we need to read the sources, R2, R6. Well, both of them look valid. We allocate a reservation station entry. This is an add, so we allocate reservation station entry B and copy our sources into the reservation stations. So R2 is 1, which is valid. Value is 2. R6 is valid. Value is 6. Okay? And we need to rename the destination register of this add. Destination register is R7. I guess I didn't provide enough space for the entire register file here. So R7 now becomes invalid, and the value for R7 is going to be produced by the instruction at reservation station B, and value we don't care about at that point. Okay? So we renamed this instruction also, and this instruction becomes ready in the next cycle, so it can start executing. Okay? So you see what we did, right? This instruction couldn't have executed before if we didn't move this instruction out of the way. Because this was dependent on this multiply. And if we did not have these reservation stations, this instruction would have stalled the entire pipeline. And we couldn't have executed this independent third instruction. But now we can start executing it in the next cycle. Yes?
I understand how that sort of moves that instruction out of the way so we don't have to stall, but how does the actual logic choose which instruction goes?
Well, let's avoid that for now. Let's assume that only one instruction becomes ready. But there needs to be some arbitration logic, right? There needs to be some. So I'm not showing that logic, but there should be some logic, control logic, that picks. It's called the select logic, actually. That selects for one of the ready instructions to go there. Now, which one do you select? Let's not get into that right now. Okay. So this was cycle. What cycle did we do? We did cycle 4, right? So basically, we enabled the execution of this instruction in the next cycle, whereas we couldn't have done it before. Okay, so let's finish this renaming. Actually, let's see what happens at cycle 5. I guess I'll just put here. So now this can execute, right? So this can do the first cycle of execution. Now we're going to rename add R8, R9, write the result into R10. I'll go through this relatively quickly. R9, R10, well, R8, R9, R10. There's an R11 here that's hiding. So when we rename this instruction, we basically copy R8 and R9 into the allocated reservation station. It's an add. And we rename the destination, which is R10. Now R10 is really going to come from C, right? Reservation station C. Well, let's do the next one. And the instructions, some other instructions are currently executing. Now we're going to rename R7, R10, R11. This is cycle 6, I think. This is 2. And this instruction can also execute, right? R8, R9, they're both available over there. In the next cycle, it starts executing. And while this is being renamed. And this is still stalling, I think. Yes. So let's rename R7, R10, R11. I think it's a multiply, is that correct? Yes. So now we're going to allocate the multiply entry. So R7 is this, 0B, squiggly, R10, 0C, again, squiggly. So 0B, 0C. This instruction has none of its sources ready, right? So it's sourcing registers R7 and R10, which are renamed to reservation stations B and C. So the values are going to come from B and C. So when the instructions B and C complete, they're going to broadcast their tags, and we're going to match the tags with the tags that are here and capture the values. And I'll show you how that happens with a few instructions too. But let's first finish renaming all of these. R5, R11, R5. I guess this cannot execute, so it's going to stay in the reservation stations for a while. And these are executing now. R5, R11, R5. And that's an add. So add R5 is 0A squiggly, R11 is 1 squiggly 11. I guess 0, A, R11 is what? 1. Okay. I didn't make a mistake. And it's writing to R5. Right. So now we need to rename R5. So all we need to do is change the tag to D. Now any other instruction that comes afterwards that sources R5 should get the value from D. Right? Because in program order, this is the instruction that's producing that value. Right? They should not get the value from A, which was the previous name, if you will, for R5. Does that make sense? So we've eliminated the output dependency this way. Any other instruction that's coming after this will get the value from D, whereas any previous instruction before this should get the value A. And how will they get that value from A? Right? Well, it's here, right? We already linked this instruction that's sourcing R5 before it was written, which is this particular instruction itself, actually, in this case, using the name A. Okay? So now we renamed all of these instructions. Now let's see what happens when this instruction actually finishes execution. 6th cycle. Well, actually, these two are finishing at the same time. And these are going to, I think, stall. I'll just call it stall. So when this multiply finishes its execution, what it does is it broadcasts its value and the tag. So multiply and X, remember, actually, another thing that the reservation station should contain is the tag, which is X. So what it does is it produces a value, and in this case we know kind of what the value is, right? What is it? 1 times 2, 2. At the end of the cycle, at least, it will become 2. And it has a tag, which is X. So it broadcasts this tag to all of the places in the machine that need that tag. Which means, I guess I'm going to make a mess here, but so this tag is broadcast to here, 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 here. Right? And any tag entry here is compared to the broadcast tag. Again, this is content-associated search, right, for each of the structures. And any matching tag captures the broadcast value. So actually, the value is also broadcast. Right. So if the tag matches the broadcast tag, value is captured in the value field. So where does this happen? Well, look here. X is being broadcast in that cycle. At the end of the cycle, there is a match. So this value bit is set, and the value is captured at the end of the cycle. It's 2. Right. Where else do we have X? Well, do we have X here? No. Do we have X here? No. Oh, we do have X here. R3. X matches. Now R3 becomes valid, and value is 2. Right. So any other instruction that now is being decoded can get the value from the registrability state because it's produced now. Right. And nobody else was writing to R3, as you can see here. Right. So any other instruction that comes here at this point, at the end of this cycle, can get the value. Okay? So now what we have done is we have enabled the execution of this instruction. Now if we can somehow build logic that at the same cycle, enables the execution of this instruction. You can actually start the execution of this add here, right? Of the second add here. So both of its sources are ready, and I'm assuming that you can have this logic. It can lengthen your critical path, but let's assume that for now. And this gets into the design of the out-of-order machines. It can become complicated. And this instruction can start executing here. Right? Make sense? Yes?
This is assuming we have more than one adder, right?
This is assuming you have more than one adder.
There's another adder instruction.
No, the pipeline adder. Yeah. You can pipeline the adder and the multiply. Okay? So in the same cycle, something else happened. This also is broadcasting its tag. So what is this instruction? This is the adder add that's writing to R7. Which one is that? That's this one, right? B. I should have renamed them better there. So now tag B is also broadcast. Which means that you need to have tag broadcast paths and value broadcast paths in parallel. That goes everywhere again, right? So for all functional units, you have to have this path that broadcasts the tags everywhere in the machine where the tag is needed. You have to send it everywhere, otherwise you lose a dependency, right? It's not a correct machine. So the same thing happens. The tag that's being broadcast is B. The value that's being broadcast is the result of the add. 2 plus 6, 8. Right? So where's B here? There's no B here. There's no B here. Well, there's a B here. So this capture, well, I don't want to delete it, but this captures the tag and captures the value 8. But it cannot become ready for execution because there's another source that's not ready yet. Right? So this will need to wait for its next source. Second source. Okay, so what happened here? Now we can start execution of this. And what is this? And these will still need to wait. Okay? And in the next cycle, these instructions write their results perhaps into the reorder buffer, although I don't want to show that here right now. Now, in the next cycle, this instruction broadcasts its tag, right? What is this? It's writing to R10. It's an add that's writing to R10. It's the add that's at C. So it broadcasts C, and the value is 17. Again, anyone waiting for C, I guess I missed something here. Somebody was waiting for B here, right? So this becomes 8 also in the previous cycle. Okay. So anyone waiting for C captures the value. Who's waiting for C? This R10 is waiting for C. Captures value 17. Who else is waiting for C in the entire machine? Whoa, this instruction is waiting for C. So it captures the value 17. Now in the next cycle, this instruction can start executing, right? Because now that both of its sources are available, so what is that instruction? That's the multiply here. So this instruction can now start executing. 1, 2, 3, 4, 5, 6. So I think I will just complete this. 3, 4, right? And this instruction needs to wait until this instruction broadcasts its tag, right? And it broadcasts its tag at the end of in this cycle. I don't remember what cycle it is, but you have it in your notes that I show over there. And this instruction broadcasts the tag, I guess, what was this multiply? R11. It broadcasts tag Y, and the result will be 8 times 17. Okay? And that's tag Y is broadcast everywhere. Did I miss something? I guess it's okay. Yeah. I guess I must have forgotten to rename one of the instructions. Is that correct? Or this is writing to R5. Oh, R5. Oh wait. This is multiply. Okay. What did I miss? Anything? R7 should have Y. Is it good? So here we're broadcasting R11. And this is waiting for R11. Somehow this didn't get R11 correctly. I think I forgot to rename this one, right? This should be Y here. And this should be waiting for really Y, right? Does that make sense? Okay. So when Y is broadcast, this captures the value, which is 8 times 17. I guess it's 136, right? Yes. And this should have been already ready, actually. And then it starts executing at this point in time. And I'll let you go through it because we're kind of out of time. But if you do all of this, then you will see that this takes 20 cycles to execute. I think it's somewhere here. Yeah, it takes 20 cycles to execute. So you actually save, I think, 5 cycles compared to a machine with aggressive data forwarding. Okay? So you've hopefully seen how this works. So you can, to summarize, renaming, we've eliminated false dependencies, and we've linked the instructions together. Tag broadcast, we've enabled value communication between dependent instructions. That's what enabled the data flow. Renaming also linked the instructions, right? Basically, we've created somehow dynamically built the data flow in the program. And we will start from there next time. I guess that's going to be after the exam.